Great. So it's work. Yeah, now it's working. I'm going to talk about TMA operations and how we use the open sky data in order to evaluate the TMA performance in terms of noise, fuel, and emissions. So you're probably already aware of that aircraft noise may affect the well-being of people that are being exposed to it. And the World Health Organization has a recommendation of a maximum of the average noise level of 45 decibels. So we wanted to look into what is the possible noise reduction gained from performing a continuous descent in a TMA, where the aircraft are continuously descending without leveling off, and also what are the savings in terms of fuel and emissions by performing a CDO. And this is a continuation of the work that we presented on the previous Open Sky Symposium, where we looked into other aspects of flight performance, and we evaluated that for 3 European airports. So the airports we were looking at is Dublin Airport in Ireland, Stockholm Arlanda, the main airport in Sweden, and Vienna in Austria. And you also see that the runways that we were looking at, and they all use different kind of systems for approach. So point merge for Dublin, the vectoring for Stockholm Arlanda, and the trombone procedures for Vienna. And these 3 airports have in common that they have roughly the same number of yearly movements. And as I said earlier, we were interested in looking into the operations within the TMA. But for Dublin, we used a 50 nautical mile circle instead, just to cover a better area of the traffic, because it doesn't extend that much to the east. I'm just going to go through very briefly about the airports. So Stockholm Arlanda has 3 runways and a parallel pair runways, which are used during the busy hours. It has a mix of the closed and the open stars. And so we were looking at runway 01 right, which has the open loop vectoring, where the aircraft are going to an initial approach fix, and then they are being vectored towards the runway to the final approach. And for Vienna, airport has 2 intersecting runways that are used simultaneously. They have the trombone procedures, which are used for path stretching and shortcuts. For Dublin, also has 2 runways, or by now actually 3 runways. They just introduced a second parallel runway, but for the time that we performed our study, or for the data, was valid for when it had 2 runways in operation. So it's operating with a point-to-point merge procedures, which has a point merge system with sequencing legs, where the aircraft are flying at level flight until the decided separation is achieved, and then they are supposed to turn towards a merge point prior to the final approach segment. So over to the methodology. So obviously we use the Open Sky database for the data, and we use the states data and use the parts of the trajectories inside the TMA that we are interested to look into more. And we used the month with the highest number of arrivals, which was October for the year 2019. We also used 4 full weeks. Before we actually use the data to evaluate and to model, we performed some cleaning steps to fix some incorrect positioning, and also to smooth the altitudes, and we removed a couple of flights, for example, non-commercial flights, helicopters, and so on, and the trajectories which were not complete within the TMA. So as I said in the introduction, this is a continuation of the previous paper, and we also then used the same data set that we used for that work, where we looked at the peak time periods in 2019. And you can also see the number of flights that we have in the respective data sets for the 3 airports here. So this figure shows the complete trajectories for the 3 airports, for Arlanda, Vienna, and Dublin. So the idea is to create a unique reference continuous descent operation profile for each flight. And then we compare the metrics for the actual flights compared to the operation of the CDO trajectories. And it's BADA version 4.2 is the core for all the modeling. And the figure you can see now on the slides is an overview of the layout of the different parts that we use for modeling. So we use the OpenSky data and then we cleaned it, as I explained, and we feed it into a tool for thrust, fuel flow, and CDO calculations, which is based on BADA equations and BADA formulas. And this tool also considers the actual weather conditions at the time of operation. So, for example, wind and temperature. Yeah, move forward. So for the performance modeling of the actual trajectories, we used the total energy model from BADA. So we considered the actual atmospheric conditions in terms of wind and temperature, but we did not consider the effects that may be caused by flaps and slats on the landing gear. For the CDO trajectories, we consider idle thrust during the descent, so minimum engine power, and no use of speed brakes. And in order to obtain a speed schedule for the descent, we use the BADA formulas where they express different speeds for different altitude ranges, basically. And then we can use the total energy model in order to find the vertical speed of the CDO trajectories for the different timestamps. And also here we don't consider the slats and the flaps and no landing gears, and we use the wind and the temperature information from the weather database. For the noise, we use the Eurocontrol impact tool, a web-based tool, and look into the LDEN noise level, which is the day, evening, night average noise, which has a couple of penalties to it depending on the time of operation of the flight. So you see on the right-hand side of the slides, you can see for the different data sets and the different times, how many operations actually belong to the different time intervals, and also you have a 0 and a 5 and a 10 decibel penalty depending on the time of the day they operated. And for the emissions evaluation, we also use Eurocontrol impact, and more specifically, we wanted to look into the carbon dioxide, nitrogen oxide, sulfur oxide, hydrocarbon, and the carbon monoxide emissions. And also here and for the emissions evaluations, we use the standard atmospheric conditions. So we basically feed impact both with cleaned OpenSky data and also data that comes from our tool for the fuel flow and the CDO and thrust calculations. For the fuel calculations, we use also BADA and obtain the fuel coefficient based on the thrust coefficient that we calculate. And then we continue using the BADA formulas in order to obtain the full the fuel flow and the full fuel consumption of the trajectory. So let's have a look at the results. So we looked more into the 30 to 55 decibels intervals, and we noticed that the levels above 55 decibels were more coincides with the final approach, which we are actually not looking into, which is not doesn't depend on whether an aircraft is performing a CDO or not, because it's following the standard procedure down to the runway for that part. And we looked into the actual area exposed to different noise levels. So we observed for every noise level a reduction in the level being covered by a different noise, as you can see in the table, in the graph to the right. I will also go through a little bit more into detail for each airport about the results later on. So these are the noise contours for Arlanda. You have the actual, the noise levels for the actual trajectories and the corresponding CDO trajectories. So the most significant noise level reductions we observed for the 35, 40, and 45 decibels areas, with between 30 and 45 additional area covered for the actual trajectories. And for Vienna, we observed for the 45, 50, and 55 decibel areas the most significant reduction, between 30 and 40%. And for Dublin, it was also the 40, 45, and 50 decibel areas, also between 30 and 40% more coverage for the actual trajectories compared to our model CDO profiles. And then for the emissions and the fuel, we noticed a reduction in fuel burn, and of course also then a reduction in CO2 emissions. And also the most significant benefit was in terms of the NOx emissions for all airports. But then when we had a look at the hydrocarbon and carbon monoxide emissions, the results varied a little bit. So for a couple of the airports, for example, you can see for Dublin has a little bit worse performance for the hydrocarbon for the CDO, which is also true for both Arlanda and Dublin for the carbon monoxide emissions. So our conclusions is that CDO contributes to noise reduction for the harmful levels that are considered by the World Health Organization. And we also observed fuel savings at all the airports when a CDO were performed, and also emission reductions, which is greatest for NOx. But as we saw in the previous slide, the emissions for CO and HC may not decrease because of CDO. And for the future work, we are going to study the trade-off between fuel and noise, and also look a little bit more into optimized scenarios where we apply automatic traffic scheduling to real scenarios to also more take into account optimization of the horizontal part of the flight trajectory. Thank you.